Abhi's family and friends. Welcome to our special occasion here. Now, for the youth, Abhi, take it away.
Perfect. Thank you everyone for coming. I'm looking forward to presenting. So my talk today will be titled Cross-Modal Transfer for Human Motion Understanding. So let's go ahead and get started. So traditionally, artificial intelligence, or AI, has been dominated by vision and language models, primarily because these modalities are how humans have interacted with computers. And as a result, a lot of large-scale text and image data sets are based on, these modalities because computer screens involve mostly text and images. However, our daily lives are filled with activities and contexts that are not always captured by screens, and we'll refer to understanding human motion outside of the computer screen as human activity recognition. So in order to understand human activities outside of the computer screen, we need AI models that can input multiple forms of data, and we'll call that multimodal AI. And with multimodal AI, there are many sort of applications we can now reach with AI models, such as in graphics, we could have improved virtual reality and simulations, and smart technology could have improved security in wearable devices. And speaking about wearables, we could also have better health monitoring and emergency notification. In robotics, we could have better autonomous systems and so on. So if our goal is to understand human activities through an AI model, the obvious solution is just to use the video and try to understand what activity the person's doing in the video. However, there are some challenges associated with video-based human activity recognition. First, video sensors are stationary. You can't have, a video camera following you around all day. That's not very practical. Second, we have that videos are sensitive to lighting, so in the dark they won't be able to see anything and they're sensitive to glare and so on. It's also very high dimensional, so to store and process this video data would also be challenging. And there's also a huge privacy and security violation if you just have constant videos of you. So as a result, the community has many other sorts of sensors we can use to give AI models forms of data that it can process, such as IMU data, LiDAR, radar, Wi-Fi signals, audio signals, and some other sorts of biometric signals as well. In this talk, I'm mostly interested in inertial measurement units, or IMU data. And IMUs essentially measure the linear and rotational acceleration in the XYZ spatial directions. And you can see here's what one would look like, and here's some sensor signals as output of that. So why I'm interested in IMU data is I think it's already quite commonplace in devices, consumer devices, such as your phones, your smartwatches, your tablets. So it gives a strong sensor signal that we can already utilize to understand motion. So if IMU data is so great, why aren't we currently using it? Well, there are some challenges also associated with using IMU data. First is the scarcity of data for training. So these large multimodal models usually need a lot of data to train, and we don't have internet scale IMU data. Second is interpretability. IMU data is relatively challenging to interpret, so it's hard to collect training labels for. So for example, if I give you this signal plot, you can't really see what activity the person's doing just by looking at it. And lastly, defining precise action boundaries is difficult due to the continuous and noisy nature of IMU data. So this time continuous data makes it such that we can't use traditional AI models with IMU data. So I pose this research question now. How can we leverage advances in vision-based activity recognition for human motion understanding across various sensors? So in this talk, I'll be talking about ways we can take a model trained with video data and somehow leverage that to perform inference with another modality, such as IMU data. Here's an overview of my talk and the manuscripts I wrote during my thesis. At the first part of my talk, I'll give a motivation and background, and this is based on a survey of IMU-based cross-modal transfer. Next, I'll talk about a method for more robust temporal preservation called cross-modal temporal alignment for human activity recognition. Then I'll talk about pairwise alignment for cross-modal transfer, which is a new method for alignment that I propose, and it's sort of a stronger form than what we traditionally see. And lastly, I'll talk about a more application-focused work called temporal video agents. And this was the work I did at my internship at Google last summer. And it's a multi-agent framework I proposed for video question answering. So let's go ahead and get started on the background for cross-modal transfer for human activity recognition. So imagine we have some smart home or smart environment setting with a camera. Currently, AI models can use video data. Hi, Professor Shing, please. Welcome. No worries. So I was talking here, we have some motivation for smart home cross-modal transfer. So currently, AI models can recognize activities from videos. Now, if the user puts on a new sensor, we can easily collect paired video sensor data with no labels needed. Now we can ask, is it possible to classify activities with just this additional sensing modality, just this IMU data when the user leaves the camera frame? So that idea here is that this video model will somehow transfer information to the IMU data model. So this brings up about this notion of cross-modal transfer learning. Transfer learning in general is when you have a model trained on some source distribution, and we're trying to leverage that model to train a model on some target distribution that's distinct. What I'm interested in this talk is about cross-modal transfer learning. So for cross-modal transfer learning, the input to the AI model is different source distributions. And in this case, that difference is different modalities altogether. And for our case here, we'll be looking at when the output distribution is the same. So that's activity recognition labels. So in my literature review on IMU-based cross-modal transfer, I proposed three methods of categorizations, these three groups in which we can divide various works into cross-modal transfer works. The first is called instance-based transfer. And in this method, we have a source model trained on the source distribution. And then during transfer, we map the target modality to the source modality. Then our target model is now just the first model composed with the second model. So the idea here is you can think of it as like data simulation or data virtualization, right? If we have IMU data and we can produce a video from that IMU data, then any model we have on video data, we can just use with that IMU data. The second method is called feature-based transfer. And with feature-based transfer, now we try to map the target modality to some intermediate representation within the source modalities model. So this is sort of like multimodal alignment or pre-training across multiple modalities and then using, a linear head to fine-tune afterwards. And you can also think of this as using backbones or pre-training. The last method we have is called label-based transfer. And here we have our target modality model mapped directly to labels outputted by the source modality. So this method is essentially knowledge distillation or pseudo-labeling. And it's widely used in these sort of works. So now that we understand a bit about cross-modal transfer, I want to dive more into what is human activity recognition. So it is sort of what it sounds like. We have a video of a person performing an activity and we pass it into some AI model F, and then we get this output label drinking here for this video. Yeah, please go ahead. Yeah. 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 So in this categorization, various works assume different things. So some works are completely unsupervised, some are semi-supervised, so they'll have triplets with labels. But based on the next section of my talk, I'll formalize that a bit more, and we're assuming that we have labeled or unlabeled pair data and labeled in one modality. Yes. Yeah. Yes. Yep. Yep. The roles can be reversed. That's correct. Yeah. Yep. Yes. Yeah, that's why I labeled it source and target for S and T right now, because I'm not defining which one's the source and which one's the target, but either of them can be the source or target. Yep. Perfect. So here I was discussing how we can sort of understand an activity. And I propose these three dimensions we can look at. One is time. So this activity can be broken down into these smaller sub-actions or atomic actions over time. The next is multiple modalities. So you can view this action in, an IMU signal, or you can see it in a video, or you can read it as text, right? So this multimodal dimension for how we can understand the activity. And then the third I propose is that we can start grouping these smaller sub-actions into more coarse-grained or more abstract descriptions of what's happening in this activity. So I call this dimension abstractness. So now using these three dimensions, I'm going to break our original research question up here into three smaller sub-questions. So how can we leverage advances in vision-based activity recognition for motion understanding? First, along time, we asked this question, how can we preserve temporal dynamics during cross-modal transfer? Second, across the multimodal aspect, we say, how can we formalize and improve multimodal alignment for sensor data? And then third, across this abstractness dimension, I ask, how can we use pre-trained models to perform abstract reasoning about human motion in real applications? So each of these research questions maps to one of my manuscripts, and those will match to a section of my talk here. So let's start off this first one, preserving temporal dynamics during transfer. The model I propose here is called Cross-modal Temporal Alignment, XTA. So this is an overview slide of this section. I'll first formalize the setting, and then I'll study a few existing methods, and I'll propose our novel approach. Then I'll test our method's cross-modal transfer performance and then test its robustness to noise. So here I want to formalize the setting a bit. In this work, I'm specifically interested in the setting where cross-modal transfer is performed without any labels for the target modality during training. So here we train on labeled video pairs and then align on unlabeled video and IMU pairs. And then during test time, we look at just the IMU data and ask, can we identify the labels here? So how I hypothesize this happening is during this first phase, we can learn some sort of decision boundary in the video's feature vector space. Then during the second phase of training, we can perform alignment across these video feature vectors and these IMU feature vectors and push them closer together. And this is sort of like, when you introduce a new sensor, but you don't have any labels, you can sort of move the representations of both those sensors or modalities together. Then during test time, the idea here is now if the person leaves the room with that new sensor, can we still recognize activities? So we propose using the feature encoder from stage 2 with that decision boundary learned in stage 1, so composing them together. And then we should be able to start classifying activities with our new sensor. So here's some existing methods for this unsupervised cross-modal transfer. First is knowledge distillation. You can think of this as the label-based transfer that I mentioned a few slides ago, but here we'll show with video and IMU data what it looks like. So we train a video model, and this is sort of our teacher model. And then during the second phase of training, when we don't have labels, we can use that video model to produce pseudo labels and then train the IMU student model with those pseudo labels. Then during test time, we can just use that student model. Then the other method I propose looking at is contrastive learning here. During training, now when we're training with labeled video data, we have this model with two stages, one video feature extraction, and then we learn an activity recognition head on top of that feature space. Then during the second phase, we can align the intermediate representations between the video data and the IMU data. And then during test time, we can string together that feature extractor from the second phase with the activity recognition head from the first phase. So now I want to investigate this contrastive learning method a bit more. This is quite standard in the literature, and I'm curious to explore how it's working and if it's working like we hypothesized. So here we visualize the latent representations, the intermediate representations for the contrastive learning method across 5 different activity classes on this UTD MHAD data set. And I'll break it down here step by step. So during alignment, in this case, we're performing the alignment phase first. These dots represent the video representations and these X's represent the IMU representations. So you can see during alignment, these dots and X's are getting closer and closer together. But what's interesting here is that these multimodal class clusters are forming before any labels are seen. So we don't see any labels, but we can see the IMU and video representations for the same activity class are starting to group together, which shows that these cross-modal structure is naturally correlated with these concepts. And I think that's an interesting result here. Yeah. So here we're just performing alignment, and the colors here are me using the ground truth labels, but I didn't include that during training, like during alignment training. No, actually, this version we're performing alignment first. So I ablate performing either of the phases first, and alignment first actually performs better. So even though I introduced the activity recognition at first. They're aligning to each other. It's like, with yeah, jointly trained. Contrastive learning, like clip with, yeah, videos and audios. Yes, yeah, that makes sense. Yeah, yeah. I think it's interesting because if you're trying to, learn representations with a single modality, like a variational autoencoder or something like that, I don't know if you'd get this nice separation as we do here. So I thought, there might be some interplay between like the cross-modal structure that's resulting in this. But you're right, it does check intuitively. Like these results aren't counterintuitive. They do align with what we think should happen. Yeah.
But what so the your representation may not be useful for anything. In fact, I use any representations and try to apply
Yes.
everything down to zero.
Yeah. Yes, yeah. So I think the way contrastive learning works with cosine similarity, it's preventing sort of this trivial mapping from occurring. And we can talk about that a little later on. I have some loss functions and stuff if we're interested. But
You do that
for this,
push things.
yeah. Yes, like they have the negatives as well in that batch. Sure, yeah. Yes, exactly. Yep. Yeah, so that's actually this next stage. That's a perfect segue, I think. Right here during training. So this is those ground truth labels after training the activity recognition head now on that aligned feature space. And when we try to predict them, so now these are our predicted labels produced from the model, this right side. And what we can see is that misclassified points often happen near the boundaries of these colored clusters. So if we draw out the boundaries as such, you can see these circles are usually overlapping the boundary. So this sort of indicates that our method is transferring that decision boundary in the lane space, as we hypothesized a few slides ago. Yeah. From the video model, yeah. So it's not seeing the IMU data at all. No, yes, yeah. So let me go back here. So during this, so for those visualizations, we perform alignment first here. So we're using these, let me do here for the people on Zoom. So we're aligning the IMU and video data here using this sort of clip style contrastive loss, like the batch symmetric one. And then after that phase, then we freeze these these encoders, and then we train this activity recognition head on those. Yes, and it's on a different set of data as well. It's not during. And we have some ablations where we try to train during, but that's oftentimes unstable. And this seems to work the best. Yes. So yeah.
Don't have the kind of scale of data.
Yes, exactly.
What you say about sort of the decision boundaries has to imply that your encoders have very small capacity, or you have immense quantities of data. Otherwise, for vast volumes of the space, the encoder could do anything right.
Yeah.
What's going to happen is the decision boundary is going to be
Yeah.
there's a mystery to explain why is that happening?
So why is it working for a smaller scale data set, you're asking?
Yeah, Clip doesn't have to answer that question because their answer is bigger resilience. Is that the next thing?
Yeah. So I think the data here might be the IMU data, I think, is highly informative of the activity the person's doing, and it makes it easier for these smaller models to understand what activity is being performed. With CLIP, like images and text are very noisy, and that's why they require a very large scales of data in order to
What's the
be able
dimension?
so here is 2048 we're using.
So you're in this fantastically high dimensional space.
Yes, for the
You're
lane space.
interpolating a function in the fantastically high dimension. Extrapolate, modeling a function, mapping it to the space. Almost no data. It should be doing funny stuff. Alex? It should be doing funny stuff. The fact that it is that there's some kind of.
So what funny stuff are you expecting? Like you don't think it would cluster this nicely, or like the boundary shouldn't transfer?
So evidence of generalization. The boundary transfer is extreme. Get all sorts of little bits of debris in their places. Or you embed in that place. I think you've got something, I think some regularization going. Something.
It might be, but when we look at the numbers, I think these visualizations look nice. When we look at the numbers, you might see that it's actually this method's not succeeding as well as we think. So this gets a 40% accuracy when we test it. So it's actually not very
so on
no, that's on the whole data set, 32 classes. So this data set's about 900 points, I think, 900 data samples for this one that I'm visualizing here. But we also have other data sets that we test on that are much larger. So in a few slides, maybe that will become a little clearer and we can run back to it. So yeah, here's sort of, I explained why these methods might be helpful, but there are also some issues with these existing methods. So my main point here is that knowledge distillation and contrastive learning methods do not effectively model time. And I think this is a type of noise that is inherently difficult for them to understand. So regardless of if we have a short video or a slightly longer one, or an even longer one, we're always compacting the entire video sequence into one latent vector. So we're compressing the data, we're losing information. What I propose doing now is extracting multiple temporal latent vectors instead of a single latent vector. And we can naturally do that using the output temporal feature maps of 3D convolutions for video data, or temporal convolutions for IMU data. And if we structure the convolutions such that we get these same number of outputs, we can perform alignment across these time steps. And this temporal latent space alignment tends to be much more robust, which I'll show in a few slides. But now, since we have a sequence of latent vectors, our activity recognition head can't simply be a linear layer because we need to be able to take in, a variable size input. So we use self-attention here, which can take in various number of tokens. And we use a class token mechanism like the VIT architecture. So that's our labeled video data training section. Then during test time, we can transfer by using this IMU feature extractor with this activity recognition head. So here's another view of the encoder. So this is the traditional alignment methods. You can see if we break the video down into these smaller substeps, it's always going to combine to a single vector. But here, our method, cross-modal temporal alignment, we condense it to multiple temporal time steps in this latent space. And the idea here is these time steps are modeling micro actions. So these output feature maps of temporal convolutions represent these learned micro actions, and we can perform alignment across these sub-actions. And the reason this architecture is helpful now is if our input video is corrupted, say for example, the last half is occluded or we don't have it, then our traditional clip style alignment will give us this single vector that's then poisoned and corrupted. Whereas our method here, now the corrupted portion only touches these last few feature vectors, because these time steps are outputs of convolutions, right? So their receptive field is only only sees the first couple of time steps of the input data. And as a result, it's robust to these corruptions and noise. Yeah. Yeah, we actually do test a transformer-based approach as well. And I think this goes back to what you and David were mentioning a few slides ago, that it actually doesn't work very well in these smaller scale data sets. And maybe as you're scaling higher and higher, using this temporal alignment mechanism for attention-based models would be beneficial. But for proof of concept here, I think the convolutions work best. And I think for attention, another problem is the corruption here would poison the output attention vector, unless you sort of mask it, because you're taking that and multiplying it by all. Yes, yeah. Yes. Yeah, you need a masked attention approach, and you need to carefully set those parameters so you're masking out relevant portions. For like 1,000-point data sets, yeah, first the smallest ones. And then our biggest one is like 5,000 points. Yeah. So here we look at the robustness of XTA based on those loss functions. So again, this is the symmetric info NC based contrastive loss, but now we have this additional sum over the time dimension. So TFM here is how many latent time steps we're extracting. And now we can see its robustness if we rename the softmax probability for positive paired to PI, and then the total sum of the losses contributed in each element as this LI. Then we can see the total sum here is the losses contributed by each element. And if we look at the loss for a single element, you can take out, say T star is corrupted. You can separate that T star vector, and you can see that the overall loss for this element would only be affected by this 1 over TFM scale. So essentially what we're making the point here is that the corrupted term's contribution for the per element loss is diluted by this 1 over TFM. So we now see that XTA's loss function is designed to be robust. And you can sort of think of this as how contrastive learning is robust to noisy captions when you have higher batch sizes. Similarly here, we're sort of inflating the batch size with this TFM element, and that's across the time dimension. That's making this loss function a bit more robust to this temporal noise as well. So now we can see the results of unsupervised cross-modal transfer. And again, I want to reiterate, during training, we have labeled video data and unlabeled IMU and video data. And then during inference, we just have IMU data and we're trying to predict the labels. So these are our data splits. So these are the results for XTA, contrastive learning and knowledge distillation, and then randomly just guessing the class. And here we can see XTA outperforms the baselines by 13% on average across 4 diverse data sets. So we can see a huge jump. And these data sets encompass various sort of scenarios. So MMEA is a egocentric camera, where the rest of these are third-person viewed cameras. And MMACT here also has various scenes and occlusions and so on. And the other part I want to note here is that all of these baseline methods are achieving zero-shot cross-modal transfer. So despite their poor performance of only 12%, that's still 4 to 9 times better than randomly guessing. So knowledge distillation is still performing in this challenging setting of having no IMU labels during training. So here we decrease the latent vector size of the models, and we notice how the size of the models decreases and the performance. And you can see that XTA maintains superior performance with smaller models, and this is valuable for resource-constrained wearables and embedded devices. We now try to test XTA's robustness to temporal variations. So here we perform crop and shift up to 50%. So we randomly take the sample and then we crop it and shift it by anywhere from 0 to 50%. And this is supposed to mimic the action being only half captured or getting occluded in the second half of the video. The next is misalignment, where we perform crop and shift on only one modality, and this could be such as hardware asynchronies or differing frame rates between the modalities. And then the third is dilation, where we crop and then we upsample this sequence. And this is supposed to mimic the same action being performed quicker and slower. So here are the results. And this table shows the accuracy decrease as well when we randomly apply this noise during training and testing. The last column reports applying any noise with equal probability. And our main insight here is we can see that the knowledge distillation and contrastive learning methods are limited. They work on well-defined data, but they don't capture temporal dynamics well. So if you look at contrastive learning here, it drops to 2% from its performance of 40% here. So that's a 90% decrease on misalignment, which I think makes sense as well, because the point of contrastive learning is to align these mechanisms. So if you have different alignments, it's not going to learn anything. We also see that XTA preserves a temporal structure. It captures how activities evolve over time and allows for the stronger real-world transfer across these modalities. Yeah, question about yeah, training and testing, and they're randomly applied. Now we visualize the self-attention weights. And for the same input, you can see it's paying most attention to this third temporal latent vector and this seventh one here. Now, if we crop and shift that input, you can see where it pays attention to also shifts proportionally. So this shows that our self-attention head is correctly learning to pay attention to when the action occurred, not just what action occurred. And these latent time steps preserve relevant information during transfer. So I want to recap sort of the main takeaways of this section. Again, at the beginning, we asked how we can preserve temporal dynamics during cross-modal transfer. Well, we learned first that feature-based cross-modal transfer is an effective method. And that was, again, those Tissot plots that we saw. Then we learned that the XTA's temporal structure allows us to preserve the time dimension during multimodal alignment. And lastly, we saw self-attention enables XTA to handle real-world temporal variation. So we see this robustness to temporal distortions. Next, moving on to this next section of our talk, we'll answer this question: how can we improve multimodal alignment for sensor data? And we propose this method, pairwise alignment. So how can we formalize and improve multimodal alignment? Here's sort of the subsections we'll go through in this section. We'll first motivate a stronger form of alignment, then we'll formalize the problem, then we'll derive a theoretical solution, show it works on synthetic data experiments, and then transfer to real-world data experiments. Multimodal alignment is commonly done through symmetric-based contrastive learning. So if you have a batch of images and corresponding captions here, and line them up accordingly, you can see you'd want to maximize the similarity of this diagonal and minimize the similarity of all the elements in the dot off diagonal. And when I say similarity, we often use cosine similarity for alignment. So this is the normalized dot product between the feature vectors. And there are multiple ways to interpret this, including maximizing the similarity between two vectors or the mutual information between the two vectors, or minimizing the angle between them on the hypersphere. I asked this question: is the contrastive, is this cosine similarity objective making the vectors equal to each other? So we saw in our lane space representations that the dots and X's for corresponding elements, although they're grouping by class, they're still quite far from each other. They're distinct points. If they were perfectly aligned, we'd get this overlap where the dots and X's are exactly on top of each other. So I ask, can we do better? And before I dive into the theory, I made this first key observation that should these modalities align exactly, or should there be a difference? So when we look at typical contrastive alignment for images and text, the same concept should map to multiple instances of the other modality, and same for text and sensor data. But In this section, I argue that for sensor-to-sensor alignment, it's a better model to have a direct one-to-one correspondence. And the idea here is that if I ask someone to perform the same action twice, such as swiping your hand left, then where the person starts every time, how fast they go will be a little different. The sensor readings will be a little different. And that's because we're working with continuous data, continuous like variable. So here we see that the sensor data instances should have a bijective correspondence in their shared latent space, even within the same concept class. Yes. Yeah, so this would, that would assume, I guess, that like occlusion would be a sort of noise. So yeah, we wouldn't want to learn that in this model as well. And different camera views would, I guess, need different sort of encoders. But I think there's some aspect of this that still improves performance or helps improve performance when we model data like this. So here we have our observed sensor data, our video, and our IMU streams, and we're going to come up with a model for this alignment mechanism. We want to learn these transformations A1 and A2 such that the latent concepts here, these dots and X's for the modalities overlap exactly. So where did this concept space come from? We propose that there exists some ground truth abstract concept space, and there are some transformations in nature's S1 and S2 that's generating our modalities. And we're sort of trying to learn this inversion from that, from those natural transformations. Yeah, did you have something?
Yes.
This one? This one. Mm-hmm.
What you're saying is the crosses on
Yeah. Yeah.
your zero zero is not the constants in the narrative. The directions align.
Yeah.
Just the magnitude.
Yes, yeah. Yeah, in the cosine similarity laws, yeah. Yes.
If you
That's an interesting question. So, are you saying like the alignment uniformity, like the sphere, and then seeing if, yeah, that's an interesting question. I don't have the plot for that for this data, but based on, yeah, so maybe the transformation I show is that like in this, like I'm motivated, having that decision boundary in the lane space and transferring. So using that sort of idea, this cosine space, assuming that this decision boundary maybe accounts for magnitude, or maybe it doesn't, but assuming if it did, then yeah.
so magnitude of that.
Yes, yeah. And I think there's some arguments to be had as well that modeling a latent space with magnitude might have some benefits as well, which,
That's
yeah, sure, sure. Yeah, I'll show you. So this is, in a few slides, I'll show you how we can do better in sort of this plot. And you're right, maybe if we view it in different sort of mechanisms, we'll see different results. Sure, yeah. Did you have, okay. Yeah. So we never visualized that exact hypersphere. Yeah, we only did Tissot here, but yes. Yes, yeah, and we actually have those scores later on. We have the cosine similar. So no, those aligned pretty well. But we argue in that we can get better cross-modal transformer performance if we get it to align in this sort of Euclidean distance sense as well. And I'll show how we can do that in a few slides. So no, I didn't visualize the sphere. So I don't know about that specific visualization. But the cosine similarity score was very high, and I'll have that in a few slides for this method. Okay, so going back here to modeling the data, we have this sort of mechanism, right? We have this estimated concept space that we're trying to recover where we want these dots and X's to overlap. And we have this ground truth abstract space where that's sort of generating our modalities that we're trying to recover. So here we define pairwise alignment as follows. If we denote X1 and X2 as the data spaces and Z is their shared latent space, given a data with paired instances of X1 and X2 and two encoders F1 and F2, we achieve perfect alignment for every instance in the data set if the encoder applied on the modalities, like those paired modalities individually, equals the same Z vector up to some invertible transformation R. So this is what we're defining as pairwise alignment. So again, here we're not normalizing beforehand. So here we assume a linear transformation model to derive our first solution. And when we do such, we can see that this S matrix, we can use essentially a matrix multiplication for modeling this data generation. So we say Z is of K dimensions and X is of D dimensions. And now we're trying to recover A1 and A2 such that A1 X1 equals A2 X2 for every element in the data set. So here we can see our A1 and A2 matrices are dimensions K by D, so the latent space by the modality space dimensions. And to get an X matrix now, for every element in the data set, we can stack them and get this large horizontal matrix. And then we can use this, rewrite this equation to just as this matrix equation, A1 X1 minus A2 X2. And with this equation now, we can factor out the A matrices and the X matrices as follows. We can concatenate A1 and A2 horizontally and stack X1 and X2 vertically. And we get this nice function here, AX equals 0. And the goal is to find non-trivial solution. So A not equal to 0, that satisfies this equation. So if we write out this objective, we can see each of these A vectors, each of these horizontal vectors in the A matrix, when you left multiply it by X equals the 0 vector. So we're essentially trying to recover vectors in the left null space of X. So to do that, we can take the singular value decomposition of X and then look at the last K columns of the U matrix. And we're doing K because we want a K-dimensional latent space. And then we can simply stack those to get our A matrix. And what we see with this formulation is now, if our left null space is greater than K dimensions, this mechanism will extract K linearly independent basis vectors in the left null space of X because those would align with those 0 singular values. And additionally, if our left null space is less than K dimensions, we can see that these would correspond to the lowest signal component. So we'll get the best approximation or the minimization of AX in this Frobenius norm. So now some insights here is that we can use our intuition about linear algebra to understand alignment. So if we have a lot of data points, we'll have a wide X matrix and the left null space is smaller and alignment's more difficult. If our modality is of high dimension but has fewer samples, we have a tall X matrix, and it's easier to perform alignment. Yes, yeah.
Because even I'm saying I do a wave and the image fix looks exactly the same, I could have some noise in my IMU, it could look different in some spaces. So there isn't exactly a, if you assume that there's some direction, my guess is it doesn't matter too much, but I'm just wondering if you have any thoughts on how.
Yeah, so we don't want noise to be captured in the alignment phase. So ideally, what we propose doing is using pre-trained encoders. So hopefully that can do some denoising as well and sort of give us structured features that we can perform this perfect or pairwise alignment step on top. So that's one way we can handle noise, and we can see it is a little bit robust. We have some theoretical experiments in the appendix slides as well, where we add Gaussian noise to synthetic data and see that it can handle a bit of noise, but we don't want that to be captured in the alignment itself. Yeah. So now we'll test this method with some synthetic data. So let's assume we use a two-dimensional Gaussian mixture model and we fix these priors, means, and have a standard covariances so we can visualize this on the right here. And this is our ground truth latent space Z. So now we can come up with these random transformations S1 and S2 just for our synthetic toy example. And we can apply that to all these Z points and we'll get our paired data set of modalities X1 and X2. And now with this paired data set, we can formulate AX equals 0, recover A, and then break our A matrix back up into transformations A1 and A2. And now with our recovered A1 matrix, we can project our data points X1 back and see if we can recover our Z data points. So here on this top right, these light blue and red dots are our recovered latent space, and the dark blue and red are what the ground truth latent space was. So this is what we recovered from modality 1. And then this is what we recovered from modality 2, and now it's indicated by X's. So if we align these together, we can see are the latent spaces the same? Are the recovered latent spaces the same? So here, the dots and X's overlap exactly. So we see that we are achieving our pairwise alignment objective. And again, just to interpret this graph, I'll reiterate these dots are the recovered latent space from modality 1, the X's are from modality 2, and the light ones are the recovered space, the dark ones are this ground truth space. So we can see that we didn't exactly recover our ground truth Gaussians because during our transformation process, we didn't have any prior knowledge about the Gaussians distribution. However, we see since it was linear transformations that we still get the Gaussianity in this new transformed space. So we can imagine that if we can form some boundary in the ground truth latent space, that we can also form some boundary in our recovered latent space. Now to quantify these results, we simply look at the distance between the dots and X's here. So the distance between our recovery from modality 1 and modality 2, and then look at their average distance here. And now we can see this table. So pairwise alignment is being performed precisely here. We can see we achieve essentially a 0 error. This essentially numbers are just going to be floating point error at this point. So it's 0 theoretically. But for contrastive learning, you can see for the regular cross-modal alignment error has a pretty high error. But when we normalize it and then take the distance, right? So that's again like the distance on this hypersphere, we get a much smaller error. So now we can see we're getting that boost while still preserving the magnitude during alignment. And this could have implications on interpretability and confidence estimation and preserving the magnitude of the vectors in the latent space. So now if we want to try applying this on real data, which is much more high dimensional and noisy, we propose pre-training encoders, F1 and F2, and we can do this based on contrastive learning or based on variational autoencoders or masked autoencoders, or any sort of pre-training mechanism. And then on this latent space now, we perform our pairwise alignment step as this sort of post-training fine-tuning step. And the full transformation for this X1 data to the latent space would now be F1 composed with our A1 matrix. So we test this method, yeah. Yeah. Yes, yeah. Yeah.
Does it peacefully or does it integrate? So on the other end, imagine I move my hand behind my back, you cannot see my hand.
Yeah.
The camera only sees my body.
Yeah, I see.
So all same image, I have all possible motions of my.
Yeah,
Everything will collapse to see. It's
I
the
see.
worst case scenario.
Yeah,
That's
yes. Yes.
what in the real world, there will be these kind of illusions. So
Yeah.
that's the spectrum. How much binary it is, does it remain robust as you increase the impose?
Yes. Yeah. Yeah. That's definitely a good, I think, thing to consider. And yeah, I believe so. In this data set that we're using, I don't think there's occlusions like that where just it moves. And I think the interesting thing to think about is like with this time series data, even if your hand is occluded and moving, if you take two videos, those videos are going to be different as well. So no, like the same camera twice, right? Like if I take a video of you moving your hand behind and then I take another video, the likelihood that the exact same pixel values are going to be there twice it's unlikely, right? So the question is like, do we want to capture that information though? Because that would be noise in terms of what we're fitting to.
And I'm walking up.
Yeah.
And I'm going to sit my hand.
Yes. Yeah. Yes. Yeah. Yes. Yes. Yeah. Thank you. Yeah. So the results we see here for this cross-modal transfer task, it's the same sort of setup that we saw in part 1 of the talk. And we can see the top 1% accuracy increases by about 5% when we do this post-training step on the encoders, this pairwise alignment step. And when we visualize the latent space here, these dashed lines connect corresponding dots and X's, and we can see if we measure the distance between the dots and X's in our perfect alignment space or alignment where we did this pairwise alignment space where we did this pairwise alignment step, that distance decreases by about half. So it is bringing them closer together, but because of noise, we're not getting the synthetic results that we saw where it's perfect overlap between these points. But we believe it is encouraging the model to align better. And here we essentially conclude that pairwise alignment can help improve cross-modal transfer performance. Yeah. It might just be Tisney is a random visualization, but depending on the parameters of Tisney, right? You get different visualizations every time you run it. So it could be this one has different. So before actually I was using contrastive alignment, right? So it's going to be normalizing the vectors and keeping that magnitude small. So here maybe it's disrupting that because of how it's trained with that perfect alignment step or pairwise alignment step. Yeah.
I find this.
Yes. Okay, so some key takeaways for this section is the main research question we're looking at was how can we improve and formalize multimodal alignment for sensor data? So we propose a strong formal alignment for one-to-one correspondence for sensor data useful for cross-modal transfer. Then we show given linear assumptions, we can leverage our understanding of linear algebra to explain alignment. And lastly, we show pairwise alignment preserves the ground truth latent structure, boosting cross-modal transfer performance in this real-world scenario. This third section we'll look at is along the abstractness dimension of our research question. We'll be looking at, can we use pre-trained models for abstract reasoning? So this work is titled Temporal Video Agents. And in this section, we'll first explore the video question answering task, and then we'll conduct a failure mode analysis on when pre-trained models fail. We'll motivate using AI agents for video understanding, introduce the temporal video agents architecture, and finally, we'll evaluate TVA's performance and its components. So video question answering is if we give a video and ask a large model to answer the question about the video. So video data is high dimensional, it's noisy and variable, and there's also subjectivity and nuance. And I want to tie this back again to the abstractness section, right? We're showing that video question answering is quite an abstract task compared to activity recognition, where we're just looking for one label. And there's also multiple spatial and temporal relationships and dynamics here. So here's an example of video question answering with Gemini. We can ask this question about the video. What is the number on the back of the jersey, the man who makes the first three-point shot? So it happens pretty quick here. It's actually hard for even a human to tell what the number was. So I cropped it out here in case we missed it. And you can see the back of the jersey is 5 for this person that makes the shot. Gemini says 11. And I think 11 was actually the player that passed to this person who made the shot. So then it's either looking at the wrong portion of the video or it's having trouble reading the back of the jersey. There are several issues that could be occurring. And here's another example of video in a question. So how many steps are in this indoor enclosure? This is a video of a child looking in a gorilla pen at the zoo. This gorilla is sitting on these 2 steps, and then there's 2 steps here in the middle under this one. And they get up and move to these 2. So there's about 6 steps here. Maybe if you count this top one, 7. Again, it's a little bit of an abstract question. But Gemini says based on this video, there are 2 steps, which is definitely incorrect. And what we think is happening here is that as the camera frame pans around, this LLM is reading the image frames individually, and maybe it's thinking those are different views of the same steps, or it's not understanding this motion of the camera moving around the scene. We analyzed 30 Gemini failure cases on the Minerva video question answering benchmark. So this benchmark has various video lengths, anywhere from 2 minutes to 60 minutes. So it's a very general benchmark. It's about various categories. It can be about math and science, about sports, cooking animals, short films, etc. So we're really looking at this general benchmark and trying to see if we can improve performance on it. So our failure case analysis resulted in 7 sort of categorizations of failures that we saw, 7 failure modes, and we counted across the 30 videos how many times these failures occur. The first one we call is optical character recognition, or just reading text in the scene. Second is object detection and tracking. Human activity recognition, person identification, scene graph understanding, so understanding like the spatial relationships between things in the scene, multimodal logic and planning across the scene, and temporal scoping, so looking at the relevant part of the video in order to answer the question. So we revisit our research question now. Can we use multiple specialized pre-trained models, such as AI agents, to improve motion and video understanding? So what is an AI agent? AI agents, I think, has become recently a popular term. However, traditionally in AI studies, this has been around for a while. This is my Intro to AI EC 448 textbook from about 7 years ago. And chapter 2, titled Intelligent Agents, defines as agent as follows. It's this AI system that can perform actions through actuators in some environment, and that environment release percepts or observations back to this agent, which it can read through sensors. So this sort of closed loop is this agent system. So recently, multimodal large language models, or LLMs, demonstrate strong reasoning and planning abilities. So if we give an LLM an environment to reason about and perform actions in, we call this an AI agent. So here actions can be like searching the internet, executing code, calling functions, and then the results of those calls would then be the observations the agent can make. And we'll again have this sort of loop. So here we see AI agents can better perform abstract reasoning about motion. We test this and develop a model to show such. Here's an overview figure. Traditional Gemini takes the entire video and then tries to answer the output if you just upload a video and ask Gemini a question. What we propose doing here is breaking that video in question down into sub-steps and subsections that are relevant to answering the question, and then having multiple specialized Gemini calls perform those sub-steps. And then we can get a better performance. So it can start actually answering these questions better. So here's an overview of our agentic framework, and I'll break it down component by component here. So the planning agent is designed to decompose questions into smaller actionable steps. And it's essentially trying to leverage chain of thought reasoning, which is a phenomenon where the model performs better by explaining its reasoning before answering the question. Next is this temporal scoping agent, which segments the videos into relevant crops. Then we have a clip analyzer agent, which analyzes isolated video segments. So it doesn't see the whole video, it just sees the segment that the temporal scoping agent gave to it. And these clip analyzing agents also have access to external tool calls, and I'll detail these in a bit as well. And then the question answering agent compiles the output from these clip analyzing agents, these other agents, and then makes the final decision on what the answer to the question should be. So we noticed some issues with this design. First, not all agents are needed for every query, so it was overkill, and sometimes the reasoning distracts from actually getting the correct answer. So what we propose doing is having this question answering agent as the central agent, and it can call the other agents as tool calls and decide when it wants to use the planning agent and temporal scoping agent. And we call this dynamic agents. Next, the problem we saw is that these LLM outputs are non-deterministic, especially for difficult questions. You can ask it the same question, give it the same video, and it'll give different responses every time. So we propose ensembling our framework and then taking the majority vote, and this tends to give a solid boost in performance. We call this ensembling TBA. So here are the main results of the paper. Here you can see we test the model on various we test the framework with various Gemini models, and we test the Gemini models on the video question answering benchmark. So when we apply TVA with Gemini Pro 2.5, we can see a 2.6% boost in increase in performance. And you can see this increase like sidesteps or surpasses just Gemini 3.0 and Gemini 3.0 high resolution, which shows that there are other ways to improve performance other than just developing the architecture. This benchmark was also tested against human performance, so having a user study where the humans try to answer the questions about the video, and that results in only 92% accuracy. So that's a 26% difference from using Gemini without any agents. And so we can see our 2.6% boost is now 10% closer to human performance. Here's some ablations where we try just using the planning agent or just using the temporal scoping agent. And here we view the performance by question type. So here we can see the planning agent performs much better on counterfactual reasoning and much worse on state change reasoning. So counterfactual reasoning is essentially questions that ask about hypothetical scenarios. So if something happened, then what would happen? So not something that actually happened, but a hypothetical scenario. So we can see the planning agent's best at reasoning in these hypothetical scenarios. Whereas the temporal scoping agent is bad at reasoning in these scenarios, but it's better at reasoning in state change scenarios, which ask, how does something change over time? And we can see that there's this huge performance difference between when the temporal scoping agent and the planning agent were useful. So the overall results were mixed when we added both of these agents onto our framework. And this shows that we need careful orchestration in order to get the best performance from our model. We also test various tools and ensembling. So we can see first that the Gemini Flash model benefits from having an external tool. It increases by 4.2%. However, the Gemini Pro model, actually having that external tool call did not help. So calling a separate character recognition model did not improve performance. But we noticed if we prompt the Gemini Pro model telling it has access to a tool function, and we don't give it an extra function to call, it tends to improve performance. And we thought maybe this was a coincidence at first, but we tried it with these other sort of tool calls as well. And it seems like the model has this sort of latent perception ability that we can unlock simply through prompting. So telling it, always try using character recognition, always use your object tracking abilities, and then it improves performance. We also noticed that ensembling consistently boosts performance, and this was our final configuration that gave the best result, which I reported 2 slides ago. Yes. This one?
So
about the prompting?
Yeah. If you make it use OCR2, it's worse.
Yes.
If you let it use OCR2, mostly that's better.
So when we made it use the OCR tool, it's not required to use it on every frame. It decides when it gets to use it. So
the difference.
yeah, sorry. So OCR tool without the prompt is when it has an external function call. So the model is not actually performing OCR. It calls a different function, and that function is running some other AI model which performs OCR, then gives the result back to Gemini. The prompt-based is it doesn't have an actual tool call function, so we're not giving it a function to call, but we're telling it you have a function to call. It's almost hallucinating its tool call. And we have some appendix slides as well where we show the reasoning traces and the Gemini model where we tell it to use its tools, but it doesn't have any extra function calling abilities. In that case, you can see it reasoning and it'll say something such as, I'll confirm this result with my tool call, confirmed. Okay, now this is like the correct result. So it's almost like thinking that it's using OCR when it's not by just prompting it.
So what is going on? One possible is the external OCR is done.
Yeah.
Argument is that's gone.
Yes.
So if it has got an internal, why is it getting better?
Because we think that it's hallucinating that it has an internal tool. Like, because we tell it it has abilities to perform character recognition, in its reasoning, it, maybe in the past training when it saw characters and saw how character recognition works, then, just seeing these words and seeing that, I need to perform character recognition, it is better able to scrutinize the image. So it's like unlocking these hidden, latent perception abilities through prompting. And also for the tool call, we did benchmark it. It gets about like 96% performance, just like accuracy. So the tool itself is like effective tool. It's like effective character recognition tool. I don't think it's the performance of the OCR tool, the external tool, that actually made that difference. I think prompting has been doing a lot of things with these LLMs that we didn't realize before, and this is one of those things.
But maybe to David's point, what I'm curious about is, suppose you change your input prompt and make it much more specific. Essentially tell your large language model, instead of just giving the high level prompt, give me the player that makes the 3-point shot. First, ask the model, go through every frame. Give me for every frame the player that has the player. Now, given that result, give me that right result in some JSON format. Now look at your JSON format. Now give me whom is making a shot, or when is a shot being made.
Yes.
Now, based on that result, compile the result and give me the number.
Yes. So that's exactly what our agentic framework was trying to do. So
but not adding.
Yes.
Really changing the font, making the font more specific and telling Gemini what you wanted to do in much more detail.
Yes. Yeah.
Yes.
Yeah. 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 So for this general video question answering benchmark, though, like the prompts, like the detail you want to provide is going to be different per question. So that was the role of the planning agent, right? To provide the further agents like this detailed step-by-step guide on what it should do for that specific question. So that was exactly the sort of reasoning that we were trying to follow when we were building this system.
But did you check if you change input prompts and make it more specific? Does it help? How much would it help?
For specific videos? Yeah. It does, yeah. We played around with it. Yeah.
Having a kid out the question.
Yes. Yes, yeah. Yes, yeah, we did try that. That was when we were doing the failure case analysis. Sometimes we would take that video and just put it in Gemini and change like how we're talking to it, telling it, giving it more specific instructions. And that tended to improve performance, which is why we gave that role to the planning agent. The planning agent, I can show you the prompts as well later in the appendix that we gave the planner agent, but it was instructed to create a step-by-step guide on what the question answering agent should follow when answering this question. No, it was included within that 2%. So yeah, the planning agent helped within that 2%. Yeah. Again, it's a difficult benchmark. Yeah. Cool. Yeah. So ensembling boost performance. So our best combination was using like the OCR object tracking prompt. and that gave us the 2.6% boost in performance. And when we test on different Gemini models, we can see this framework did consistently boost performance, but how much it boosted performance was different for every model. And this resulted in the, oh, hi everyone on Zoom, sorry, the computer just died for a second. Now it's plugged in and back ready to go. Thanks for your patience. Okay. Let me share the Zoom screen. Okay, we should be back and ready. Okay, so as I was saying in this last point, that testing on different Gemini models resulted in slightly different performances, although we saw some consistent boost with our framework. And this shows that, it scales differently for different sizes of the same LLM architecture. So now let me reshare. I apologize. It was not switching slides correctly. So here are the key insights for this section. How can we use pre-trained models or AI agents to perform abstract reasoning about human motion? So one, we saw agentic planning and reasoning can elicit chain of thought reasoning, which is highly effective for multimodal understanding. We also saw this latent perception paradox where we can elicit internal perception capabilities, such as tools, as opposed to using external tool calls. And we saw, lastly, that this orchestration requires application-specific details, and multi-agent frameworks should be built on an application-specific basis. So now we'll conclude with some overall key takeaways, and again, this overview of the talk. Our main research question here was how we can leverage advances in vision-based activity recognition for motion understanding. My first survey discussed cross-modal transfer from vision models to human activities, and it addressed these three fundamental dimensions of activity recognition. We had time, multiple modalities, and abstractness. So how can we preserve temporal dynamics during cross-modal transfer? First was through fine-grained feature alignment was our answer, and that was the XTA model we developed. Second, we asked how can we formalize multimodal alignment for sensor data? And this was done through a pairwise correspondence problem, and that was our pairwise alignment solution. Lastly, we asked how can we use pre-trained models to perform abstract reasoning about motion, and we saw that effective reasoning could be done through agentic orchestration and prompt elicited perception. So some future extensions that I considered and would suggest, fellow colleagues to also look at is, extending cross-modal temporal alignment to continuous activity recognition, deployment, and other modalities and tasks. Pairwise alignment can extend to temporal spaces and additional pre-training methods, and maybe theory along nonlinear systems. For temporal video agents, adding additional orchestration or tooling agents could be helpful. And introducing inter-agent chat or communication would also benefit the system. When I was developing this work, I also wanted to consider broader impacts and ethical considerations. So with increased multimodal linkage, we should consider bias propagation across the modalities as well. And if one modality is compromised, that might pose security risks in the other modality as well. Some modalities might be less accessible than others as well to certain communities. So we should be considerate of that and think about application contexts for these systems as well. For mitigation strategies, we should be careful when we're curating data sets to make sure it's representative. We can do bias auditing during development and deployment. We should have privacy-aware deployment and monitor ongoing development and community engagement. So I would like to make some acknowledgements. First, I would like to thank my professor, Min Do, for all his support throughout these years. I think he helped me grow as a researcher and as a person as well in general, and I think it was a great journey for me. I'd like to thank all the other committee members for being here and providing their support and feedback in my thesis process. I'd like to thank other faculty mentors I had in the department, as well as collaborators on my papers. Shout out to them, a huge thanks for their support in writing these works. And My funding is through the National Science Foundation Graduate Research Fellowship Program, the NSF-GRFP. And last but not least, I would like to thank the community, so my lab mates and colleagues, all my friends throughout these years, and my family as well for being there to support me. So thank you all for listening. This concludes my talk.
It's open for any additional questions. Meeting members as well as the audience.
I have just two high-level questions. So first, maybe building off that the last slide or two. So I think in general, it's good to think about with PhD theses, like what is the remaining work to be done if someone wanted to like transfer this to practice. You kind of know some things, but I was wondering if maybe you could just comment on like what is the gap between what was done in this sort of academic research setting and if someone really wanted to deploy this in some systems. What needs to be done, and if there's anything that might change, like maybe you don't want to worry as much about accuracy, you'd rather worry about precision or something like that. Is there any other considerations if they were to like read your thesis and want to deploy it?
Yeah, so I think there are a few things. I think in a lot of my work, I was trying to look at the theory and fundamental understanding of why something works and how it works in these toy scenarios. So I think if we want to apply it, the first thing we should do is scale. So try, with larger and larger data sets, more data, more modalities, more noise, occlusions, things like that, and see if we can maintain accuracies in these sort of insights that I gained are holding under these assumptions, and maybe you'll need to tweak things in the architectures or you'll realize things that we didn't see before. And then while scaling, I think thinking about how it would actually be deployed is important as well. So I think I motivated like the smart home setting for my first two projects, maybe trying it out in an actual smart home. I think the data sets I worked with were still segmented into like one action and then another action. And I imitated noise by cropping and shifting it and so on. But in a real life scenario, you would have one continuous video with multiple actions that fluidly transition between them. So seeing if you can extend this architecture and apply it under that continuous time system, I think would be important as well. So I think scale and working with continuous time data is important for sensor data. And I think that's one of the main challenges that we're seeing in the field and the community. I think a lot of these models developed very well for images and text and videos. And if we try to use it on sensor data and robotics applications, it's much harder to use on that sort of time series data. So that's sort of those two aspects I would try to focus on.
So maybe just
I don't know, it's time to add some context about what is the future.
Oh yeah. Yeah, I was debating putting all the slides around. So after I graduate, I'll be joining Waymo on the sensor simulation team in August. So yeah.
Continue, I guess, a lot of work about.
Yeah, so I would be really curious to see if I can learn what I applied about processing continuous signals there as well and continue to investigate how we can train AI models to process sensor data better and work with time series data, which I think is a really interesting open-ended problem. And I think there might be better architectures than transformers and convolutions out there that are yet to be discovered. I can't reveal that information. Top secret. Yeah.
yeah, maybe one. Which may actually not be relevant, but so it seems like a lot of what you've been working on is like in this realm of classification or some kind of answering, but basically it's like there's set input maybe it's over time, but then you have your and because in cross-modal transfer, there's some work in more like decision making, robotics context where it's more online and adaptive. That kind of something more suited with like action decision making.
Yes.
I wonder if there's any like, connections or what's the relationship between the stuff that you've been working on to the more like online adaptation, or if there's any insight that you see.
Yeah, I think that's important to think about as well. I think in online learning and continuous learning, we need to think about how we can, keep a stable system with this sort of, I guess, high level noise in the video data and with the sensor data. And I think we might need to look into other sorts of methods like reinforcement learning maybe and see if we can introduce this sort of temporal alignment or time steps into RL as well and other sorts of online algorithms. I think that would be an interesting sort of extension in future work. Yeah.
Could you put the results in context to how the related work and the related? One thing I didn't see the patient of other work applying, we're using the same data that's showing the results, seeing how the results compare to them.
Yes, yeah. So I think one of the main works for one of the most popular works, I think, that does this across multiple modalities is ImageBind. If you're familiar, they perform contrastive learning and they align images with multiple modalities like audio, thermal cameras, and they also use IMU data. And the results there are more focused on, cross-modal retrieval and looking at semi-supervised methods. So if we train a linear head now on top of this learned IMU encoder, can we perform better? They don't have this sort of zero-shot transfer to another modality for performance. And the interesting thing there that I think makes it hard to compare with these methods is a lot of them align with text data, which I debated whether aligning with text data was a good idea or not, because you're introducing now labels, like the label is in the text domain. And the idea there is that text is this discrete modality. So aligning over time, like you can't break it into temporal tokens, and you're essentially losing the time dimension when we perform alignment across there. So it is quite difficult to compare directly to those methods. Let me see if I can pull this slide up. This was one of the hidden slides. The ImageBind result on Ego 4D for this sort of zero-shot cross-modal transfer result was 25%. So of course it's a different domain. They're using higher, much more data, Ego 4D, more noisy, but it was hard to compare 25% to the 40% accuracy we saw in our data sets, like for our sort of zero-shot transfer method. IMU2 Clip's another one, IMU2 Clip, and they do this zero shot, again, about 24, 25% accuracy, 30% accuracy. So it's a low accuracy domain, which is why it was one of the reasons I was interested in studying these problems, because I think we're really not there yet to where we can use IMU data in application settings. But it was difficult to compare in the same table, although there are other methods that try to do the same thing. And most of those papers focus on a different aspect, and the zero shot is just like additional experiment on there. And they align with text data, which arguably violates that zero shot setting. Yeah. Mhm. Yeah. So I think it was a trade-off between running more experiments and understanding why it works on these smaller scale data sets and going into the realm of scaling and seeing if it works on scale data sets. And I think in my future, now that I'm going to a big company, I'm sure scaling is going to be a much more important thing. And most of my work is going to be how can we scale this? How can we make it work in real world settings? But in this PhD, I think it was my time to step back and visualize on these small settings, why it works, how it works. Can we come up with theory bounds, ablations on these small settings, and so on. And yeah, I think Ego 4D, which we saw just in the last slide, is the biggest IMU data set. It's not really labeled, it's more like text descriptions, but there are versions where people take it and then produce labels for them. So you're right, there are larger data sets we could have used, but it's that trade-off of trying to make it work on a large data set to get the number, or seeing if we can understand it.
So just for baseline. The old-fashioned thing to do for IMU data is vector quantizing. Get a histogram of the centers,
Yeah.
and you plug that into these kind of data sets. We get
I haven't explored that exact like feature extraction method that's not learned. I think I explored learning a very simple like linear layer or doing a VAE pre-training and then trying to learn like a linear boundary on top of that VAE model just on the IMU data. So I did these sort of small explorations, but I didn't do any classical like handcrafted features where you try to see it how well of a boundary you can get. And for like let's see how far is my actual. This is my actual page. So for this data set is the one I used quite a bit for these sort of toy experiments. You can train a supervised method with like 96% accuracy, 97% accuracy.
so. Used to ask curious question. Deal with small data sets. Feature learning is too expensive. One of the things, one is you find two, and the other is you go feature learning step shooting and start using it to feature experiment.
Yes, yeah.
I'm wondering why. So you would need to use some kind of fine-tuned thing on the game saying.
Yeah.
Eligible for typical sources for videos, it's not coming back.
Yes, yeah.
But it isn't obvious to me that feature learning is actually benefit.
For the IMU data. Yeah, that's something to explore as well. And I think maybe for this small scale data set, if we assume we want a small an application where we can use less amount of data and learn a effective IMU model, like it's worth using these sort of classical methods like you mentioned. But if in the future we want someone to take this work and try to scale it, or we want to explore something fundamental that can also has the potential to scale, working with these AI models, I think.
So I'm hearing late night. It'll eventually,
Okay.
which was right.
Yeah.
But the argument that basically is if you get enough data, learning for IMU data will eventually work. It's okay.
I think, yeah, it's more likely to work than.
We're not talking about that.
Yeah.
And it isn't obvious that it's necessarily a good strategy to design particular data sets this size.
Mm-hmm.
Might use something else and then think about on the IMU side, and then continue to think about the role.
Yeah. Yes, that's possible. And again, it might be dependent on the application as well.
So a lot of the stuff said about the alignment and clustering is basically based on qualitative analysis.
For those visualizations, yes. And then we have these sort of
presentation of the clustering.
So we have a few more examples on various data sets, 2 or 3 data sets, and it was pretty consistent in terms of what we're seeing here. Yes, yeah.
And you look at saying,
yes. So you're saying like the high dimensionality made the visualization.
Action, right? Clustering aspects, so it's one.
Okay, yeah, I think here, so
I can give you an answer. It's at best suspect. It's
okay,
dangerously inclined to find clusters where
I see. So it's
giving you
biased essentially. Yeah,
well
towards
stuff,
clustering.
right?
Yes, yeah.
When you look at it makes it fuzzy inside, then you want to do an awful lot of other stuff.
Yeah. Yes, yeah. And again, we have a lot of, appendix slides with additional appellations, experiments where we check, the alignment length, we try different training mechanisms. And I think the data overwhelmingly shows that, aligning over time steps is helpful. I think the t-SNE visualization was just to motivate why we're doing this feature-based transfer. So, the t-SNE motivation, it looks nice, and I think it's a good motivation, but it's not the main result of the work, right? It was more of the feature-based transfer is good. Here's how we can do it even better than what's shown there. Yeah.
You run different data.
Mhm.
Do you see similar generalized across data sets?
Yes. Yeah, so we tried on 4 different data sets that were quite diverse here, but it's not, I guess we're not pre-training on one data set and cross data set trade separately on each of them. So the architecture is generalizing, but I think we'll need stronger, larger, more representative, more data in order to try to pre-train and then do cross data set experiments. But like I mentioned before, this data set is an egocentric one, so it is a little diverse than the Sorry? Yes, classification in that 0-shot setting where we don't have IMU labels during training, but we're trying to predict the IMU labels during testing. Here's actually a figure of the data sets we had and some statistics about them. So you can see they're a bit diverse in terms of how many IMU sensors we're using, where the IMUs are placed, things like that. And the largest one, this MMEA, is about 6,000 samples. And number of action classes is different as well, number of IMUs. So yeah, we tried out on different IMU video data sets. Yes. So this was 24.
Talking.
Yes.
Confused. Is this jointly trained? Meaning are both A and B jointly trained? Are they separately trained?
Yes, that's a good question. Let me see if I can find, the slide where we show the training methods. So we tried a couple of different training methods here. So one is, how I presented. We trained first phase A and then we trained first phase B. Then I flipped it and tried training, and this is where I got those visualizations. This method ended up working best for XTA here. You can see it. So first train and then flip and try. We also try interspersed training. So one epoch on the first split and then one epoch on the second split. And this one was a bit unstable. And then we tried combined training where we take a lot, like one batch of loss from the first set and the one batch of loss from the second data split and then add them together and try training. And that actually seemed to work the best for this contrastive learning method. But I guess in our application scenario where we have some, pre-trained video model and we're trying to transfer that doesn't make much sense there. But in this scenario, that did work better. So we presented like the strongest performing contrastive learning training method in the other data set experiments as well.
So align first.
Align first for the XTA model. Yep, so when you were asking on slide 24, yeah, for that model, it was alignment first. Yeah. Yes. Yes, yeah. Mm-hmm. Yes, for our synthetic experiments or in our hypothesis, but in reality, when we put it, it was after pre-trained learning, like pre-trained encoders. But so it's in the embedding space then. Yeah. Yes, yeah. Already, yes.
After that configuration, there's still some tightening that I can do.
Yes, exactly. Exactly, yes. 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 And I think that's a good question. And how CLIP is formulated again with those normalized vectors and how it's designed is to work across large I think so. And I think another interesting thing about clip is I think it has a stronger sense of negatives. Like you're trying to align with the positive pair and move away from the negative pair. We're actually focusing really on that positive pair and trying to collapse like the distance between them with our sort of AX equals 0 formulation. Because we're not making, one representation move away from the other. We're making the representation, like we're not making the negative samples move away from each other like clip does. Are you following what I'm saying? So clip has like the positive and the negatives. Small point. Yeah. So I guess there's some assumptions here that the uh, X matrix is, well defined, right? So it would have collapsed to 0 is basically asking like, when would the left null space just be zeros, right? For that transformation here, right? So this A transformation would collapse to zeros when the left side of this U is just zeros. So that would be the case, if we don't have a full rank or a sufficient rank matrix. And that might be the case, I think, when you said before, like if we have one element in one modality that corresponds to multiple elements in the other modality, I think then we might see some of that behavior where the A transformations collapse to 0.
So, I'm thinking about it. What you might be powerful because if there's something that you're saying that optimize even after clip.
Yeah.
And there's a linear operation that can do that. You should think of or thesis or the general out of curiosity. Can you say something clip plus plus?
Mm-hmm.
Right? As a general even after what you're doing, I can further tighten it to do things better.
Yes, yeah.
And the very localized linear.
Yes.
Like
Yes. Yes. Yeah. And I think we'd have to prove the usefulness of that tightening as well in various applications. If it's possible. Yes, yeah.
Not optimize this object.
Yes. Yes, yeah. Yeah.
Now you're moving your points closer to that object.
I want the meaning of two modalities of data to be the same. I want the modalities of data to be encoded to the same meaning that they come.
But put your finger on it. Put your finger on it. Wants to do two things. One is it wants to get things close together, but the other
Spread.
get generally other stuff spread out. And it's perfectly willing to sacrifice a certain amount of similarity to get it spread out. That's where that's
Yeah.
Yep.
Or the clip was not optimized. And he was trying to push things away. His application does not need that. But he still needs that for the classification.
Yeah.
No, but the reason the AX gets right is because of the nature of the data set. It's relative, very, and the fact that it's so far away it still doesn't want to work. You now go and say, look, okay, let's just clean them up a little bit and make them sit slightly more because I'm ignoring the fact that we're spoken about.
Yeah. And again, I mentioned before, but I think it again links back to like when would this be used for, when we would want this application. And I think clip works very well for images and text, but I'm claiming for sensor data, it might be worth exploring other sorts of objectives. It might be useful to try to get this exact correspondence in the lane space, and especially for cross-modal transfer.
I think there's
Yeah.
in images. Things can be really quite close to each other. That we see.
Yes.
Here you go categories that are really quite big distinction.
Yes. Yeah.
Well, And we pretty guarantee that if they look the same in one, they're going to look different in another.
Yes.
And that's a very, very big distinction. So the natural experiment is drop the correspondence between the ion. Right now, do one descent step by step, then use weighted bipartite matching. So just everybody joins their closest. Go again.
Yes.
Question: what happens? And I think you get the embedding that's very, very good up to a permutation between clusters.
Yes.
The reason that happens basically is your video clusters are so distinct and your IMU clusters are so distinct. It's very, very hard to get a clustering for.
Yes.
Particularly if you have one in one modality, it's hard, it's going to be easy in the other one. If we're looking at presenting, I think there's a real difference between spaces and something you can explore. One question you might ask is how good was Cliff at forcing things to spread out? Right. So in vision and text, it's not that easy because everything's quite close to something else. It's quite close to something else.
Yeah.
Here you can probably make them spread out. And it might be worth looking at those losses to see a bit different.
Yeah. Yeah, that's a great suggestion.
Well, asking questions, but having opinions. So
well, that's great. I welcome all the opinions as well. That's helpful for my thesis writing process as well.
Now, another stage that we like just the committee members to deliberate the outcome. So like here to step outside. Break out.
Sure. Thank you all for staying on. I heard back from the professors and the defense was a success. So I appreciate all your support.